Okay, this is Mike Morrow, and today we are going to be doing the Algebra 3, Chapter 3 Review Part B. Okay, get this volume turned up here. Alright, for the function graph, classify each point as absolute maximum or minimum or local maximum or minimum. Alright, we know that the absolute maximum is if the the highest point on the graph, and of course you can see that it's going up forever and ever there and there, so it doesn't have an absolute maximum. That's infinity, but it has a local maximum right there at CD. So CD is the, and my pen is again not working good. All right, CD is the local maximum. We have the minimum points here at EH and AB. Well, EH is the lowest point on the graph, so that's the absolute minimum. That's EH, all right? And so therefore the AB is the local, it is the local minimum. There you go. All right. Moving on down, problem number 2. All right, we're talking about the degree, leading coefficient, and constant of functions. All right, the degree is the highest exponent. All right, you see it right there. All right, and of course, you're looking at both the f of x and g of x. On f of x, there's the highest exponent right there. On the g of x, there's 6. So 4 and 6. All right, leading coefficient is always going to be the coefficient for the highest exponent in descending order. And of course, that'll be the out front right there and there. So 2 and negative 3. All right, and the constant terms, of course, have no variables. Negative 4 and 5. And there you go. Moving on. Problem number 3. Based upon the degree and leading coefficient, which of the following functions could be the equation for the graph below? We have to look at the shape of the graph to decide if the degree should be even or odd, and then look at whether the graph is flipped over or not to decide if the leading coefficient should be positive or negative. All right, this one is going up and then ending up down. All right. Well, up, down, if we look at our chart, I don't have it listed here, but the chart says that if it's up, down, that's going to be a leading coefficient that is negative and an odd degree. So that's that one right there. Down, or up, starts up and then goes down. That's g of x, c. All right, moving on. What is the remainder of this function dividing by x plus 2? All right, we're going to use the remainder theorem, which is taking the divisor, the x plus 2, set it equal to 0, and solve. And that's what we've done right here. You get x equal to negative 2. Then just take the negative 2 and plug it into all of the x values. You're going to substitute and then evaluate. Evaluate that, and you end up getting 0 for a remainder. Moving on. All right. The possible zeros of a function, you take the constant term, the negative 6 in this case, divide it by, or all the factors of that constant term, divided by all the factors of the leading coefficient, and that's what we have here, 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 and here. 6 has these 4 factors, 1 times 6 and 2 times 3. And the 2 out front it's a prime number, so it only has 2 factors, itself and 1. There they are. All right, and then what you do is you take all of these up here and divide them by that 1, and that's what I've got there, those 4. And then take those same 4 and divide them by 2. All right, and that's what we've got on those. All right, and here it's just if you have repeats, then you can mark them out, like 1 divided by 1 is equal to 1, but so is 2 divided by 2. They're the same thing, so mark that one out. And I see there's another one here. 3 divided by 1 is the same as 6 divided by 2. All right, and that leaves you in simplified form. I'm going to try to do this without messing my pen up here. There's a positive and negative 1. That's the first one. And then positive and negative 2 there. Positive and negative 3, positive and negative 6, 6 divided by 1 is 6. And then we do our fractions, plus or minus positive or negative 1/2 and positive or negative 3/2. Those are the positive. That is 1, 2, 3, 4, 5, 6 times 2 is 12. There's 12 different possibilities for zeros for this function. Okay? All right, moving on. Number 6. All right, on this one, if x equals 3 and x equals 2 plus I are zeros of a polynomial, then what must also be a zero? Well, just looking at the function here, that the way we get these two possible answers or solutions is, here is the function that we're dealing with. All right, it's x minus 3 and then x squared minus 4x plus 5. Set that function equal to 0. And the x minus 3, by the zero product property, set it equal to 0. You get 3 for one solution. That's how we get the 3 up there. All right, and then we're going to have to get the 2 plus I as another solution. We're going to have to use the quadratic formula with the rest of this is quadratic, and that's what we're doing right over here. All right, so plug in the numbers where they go. Here's your A, B, and C. Plug them where they go into the formula, and we see that we get our discriminant to be a negative 4, which gives us a 2i. And then when we simplify that, 4 divided by 2 is 2. 2 divided by 2 is 1. 1i. That is this. That's how we got that. Well, you notice we got 2 plus 1i and 2 minus I. All right, so 2 minus I is the one we're looking for. That's what goes right there, 2 minus I. Okay? All right, moving along here. Number 7. All right. The running pace for the fastest female runner for their age in the race for Hope 5K is given in the graph. This can be modeled by this equation given, where x is age and y is average pace in minutes per mile. So what would you predict the pace to be for a 50-year-old woman? Well, just look at the graph. We don't have to worry about the equation. Just look at the graph. There's 50 years old, and go straight up to that point, and then go straight over, about right in there. What is that? About minutes per mile, about 8.7 minutes per mile, approximately 8.7 minutes, roughly. You're just estimating. All right, moving along. Problem number 8. I think we've gotten to the bottom down here. All right, 8, 9, and 10. All we're doing is listing the zeros and multiplicities for each function. All right, so we're going to set the x minus 4 equal to 0 and solve. You get positive 4. So there's 4, but then you look at its exponent. That 2 right there means that it has a multiplicity of 2. All right, and the same thing with the x plus 2 equal to 0. You get negative 2, so there you go, negative 2, and it has an exponent of 2, so it's a multiplicity of 2 also. All right, next problem. X minus 2, set it equal to 0, you get positive 2. It has an exponent of 1, so it's just multiplicity of 1. You don't have to list that. X plus 1 equals 0, solve, you get negative 1. And it has an exponent of 2, so multiplicity of 2. X plus 4, set that equal to 0, solve, you get negative 4. Its exponent is 3, so its multiplicity is 3. And we work this last one the same way. Set the x minus 5 equal to 0, you get 5. And its exponent is 2, so it's a multiplicity of 2. Set the x plus 2 equal to 0, you get negative 2, and there you go. We don't worry about the 3 out front. That's just a constant, and it would just divide out, and we don't worry about it. Okay, so there we go.